Another way is to consider paths through the graph. And this is equivalent. This is completely equivalent. So um, we'll say that, but I think it's maybe a little more intuitive than the inductive way. So we'll say that, and again, we'll do this for every state. So we'll define the language for every state, and this definition will be equivalent to the one we just had. So we'll say that a word or a string W is in the language of state Q exactly if there's a path from Q to some state in F such that W is the concatenation of all the labels along the path in sequence. Okay? And we can put that formally by saying, well, one way to do that is to say, well, if there's some way to break our word W up into n different pieces in such a way that there's a sequence of n plus 1 states that starts at Q and ends at a final state, and the transitions along there are labeled by these little strings that we broke W up into. Okay, those strings would have to be strings of either length 0 or a length 1, right? Just because that's the only kind of label that transitions can have. Anyway, so let's look at an example. So, for example, I can prove that ABB is in the language of state 0 by breaking it up into 3 parts, or actually 4 parts. I'll break ABB into 4 parts, and the first part is just the string with just an A, and then the string with just a B, and then the string with just a B, and then the empty string is my last part. Okay, and I can observe that I have transitions that go from 0 labeled with the first part to 1, from 1 to 1 labeled by the second part, from 1 to 1 labeled by the third part, and from 1 to 2 labeled by the fourth part. And since 2 is a final state, that means that ABB is in the language of state 0. Okay? And you can do the same thing for any of the strings that we just showed belong to the to some state. And in particular, the empty string is in the language of state 2. In order to show that, I have to break it up into 0 parts. Okay? But I can do that. You can break the empty string into 0 parts. No other string, but just the empty string you can break up into 0 pieces. And and then our path just consists of a single state, which is state 2. Okay? And then we don't need any transitions, and 2 is a final state. So, so this definition, when you have to understand that each of these, it is one way to break a string up into parts is to break it up into 0 parts. If it's the empty string, you can do that. Okay. If it's a string of length, say k, then you're going to need at least k parts, because each part has to either be length 0 or 1. Okay? It's going to turn out to be useful later to think about the language belonging to a set of states. So that's straightforward. If you have a finite set of states. Of course, Q is finite. If you remember, our set of states overall is finite, so any subset will be finite. And if R is a subset of Q, we can define the language of R to be simply the language of the union of all the languages of the constituent states. Okay? That will be useful a little bit later, so get it out now. Okay. One thing about states is that they're actually arbitrary. It doesn't really matter what the states are called. If you systematically rename them, then you'll get an equivalent machine or an equivalent recognizer that means the same thing. Okay, let's say we have some state q and some other state q dot. Q dot is at least as big as q, and f is some 1-1 total function from q to q dot. So total means that everything in q is mapped by f, and 1-1 means that if I have two different states in q, f will map them to two different states in q dot. So if I do that, I can make a brand new automaton, which I'll call a dot. It has the same alphabet, but now it has q dot for its state set. It has f of q start as its start state. I'll call that q dot. That's q dot is, or q dot start is q start with, is f of q start. The final states will be the states that the final states of A map to, and the transitions will just be the same transitions, same set of transitions, except that we'll change the states using F, right? Very straightforward. So in particular, you can always rename the states so that the states start at 0 and just consist of as many integers as there are states in Q. And that's quite useful because then you can use arrays to represent things. We'll see that later. So in particular, if we take, if we take this example here, I could systematically rename those, rename the states here. That's going to turn out to be useful later. In fact, it's going to turn out to be useful real soon. In this journey to show that regular expressions and NDFRs are equivalent formalisms, the first thing we're going to do is show that any regular language can be described by an NDFR. Now we know that any regular language can be described by a regular expression, so what we'll do is we'll create a little compilation algorithm that compiles a regular expression into an equivalent NDFR. And this translation algorithm is called Thompson's construction. It's named after a guy named Ken Thompson. And I'm just going to bring up his picture here. Okay, so here are a couple of pictures of Ken Thompson. And one thing he was famous for later on was creating the world's best chess playing program. It was in fact not a program but a machine. He was one of the first people, I think he was the first person to build a special purpose computer designed just to play chess. So it was a one-off. Well, it was a one of a kind, but he kept rebuilding it and making it better every year. And for many years, his computer was beating supercomputers at the game of chess. Okay, the thing that he's even more famous for than that is here in this other picture we see him with another guy named Dennis Ritchie. So here we have Thompson over here and Ritchie. And Thompson and Ritchie are well known because they created the operating system that almost all of us use now, which is Unix. If you have an iPhone, that runs Unix. If you have a Mac, that runs Unix. If you have an Android, that runs Linux, which is not quite Unix, but it sure is similar. And if you have a Windows machine, well, that doesn't run Unix, but it runs an operating system that was certainly inspired by Unix and is getting closer to Unix all the time. Okay, anyway, so that's Ken Thompson. Very interesting guy.